Okay. Hello, my name is Deedee,
And I am August.
and today we're going to talk about optimization for matrix multiply. So first of all, this is how you do normal matrix multiply in C, and in other words, it's base multiply. So how this works is that you basically do the normal matrix multiply, which is basically 1 times 1, 2 times 5, 3 times 9, 4 times 13. You add them together, you get 90. Then you go to the next column and do 1 times 2, 2 times 6, 3 times 10, 4 times 14. After that, you add them together and you get 100. And then you do this next column, you do the same thing, and then you get 110. Another column, 120. Then you switch to the next row, and then you times it with the first column, and then the same row again, the second column, third column, fourth column, and you get 202, 228, 254, 280. And then you just keep going like that. So now the third row, and then first column, second column, third column, fourth column, and then the same thing with the fourth row. Now, how can we optimize our performance for this matrix multiplication? So for a small value of size x and size y, meaning the dimension of the matrix, it may not matter much if it's like a very small value. But if we increase size x and size y to a bigger value, like 100, 500, and 1000, it will take longer to finish computing. And this may be because there's a high cache miss rate. And we'll talk more in detail later. And therefore the computer will have to fetch more information from the DRAM many times, which is a very slow process. And so for this assignment, we were given to assume that size x and size y is 22,000, which is a very big matrix. So what can we do? Theoretically, we can do blocks matrix multiplication, where we divide the whole matrix into blocks, then do multiplication within the block before moving to the next block, and then repeating the same process. This way, we deal one block at a time. And to put it simply, for now, we just fill up the L1 cache with that block, and so that will give you a higher hit rate. And we'll talk more in detail later. And this is our computer specification. So the model is Intel, and the cache, the L1 cache, data L1 cache is 384 kilobytes. So we'll look at that later on.
Okay, so there's the format for our blocking. So we will divide each metric into 4 groups. The metric A, we have A, B, and C and D group. Metric B, we have E, F, G, and H group. And then in metric C, it will be the sum of the multiple of AE plus BG. And then the next section will be AF plus BH, and then so on. So for the explanation, we will simplify the block metric multiplication to 4 times 4 metric, and because it's 4 times 4, the B size have to be equal to 2. So this is the overview of our 4 times 4 example code. I will slowly explain the code from the most inner loop to the outer loop one by one. So this is the iteration for K loop. So because B size is 2, the inner K loop will loop 2 times in total. So it will loop 1 times 1 for the first time this loop, and then 2 times 5 for the second time this loop. And then it's add together and it gets 11. So the next one is iteration of J. Basically is repeat the iteration of K one more time. So before is 1 times 1 and 2 times 5 get 11. This time is 1 times 2 and 2 times 6 and you get 14. So now we got the iteration of I. So n n here is equal to 4 because it's a 4 times 4 metric. So with the n of 4, you repeat the j 4 times. So with that, it means that we move from 1 and 2 on the first row of metric A, move down by 1 to 5 and 6. And with that, 5 and 6 will give us 35 and 46. And then we move down one more time because there's 3 more loops in total. So 9 and 10, and then we got 59 and 78, then 14 and 13, and I got 83 and 110. So we're done with the I loop. Now, as you can see, we get kind of like the first half of our matrix C. So here you can see that it's A times E and C times E already. Now we move on to iteration of JJ. So what JJ essentially do is move the block of 1, 2, 5, 6 to 3, 4, 7, 8. Here, as you can see, this is the old block, and this one is the new block. And then with JJ, is move one more time. So we repeat every step from the K, J, and I 4 more times. So you got 1 times 3, 2 times 7, and you add together, you get 17. 1 times 4, 8 times 2, add together, you get 20. And then just continue, you move down one more row, 5 and 6, times the same block, you get 57, 68. Move down one more row, you get 9 and 10, times the same block, got 97, 116. One more row, you got the last section of the matrix C, which is 137 and 164. And if you look at the formula for our blocking, you can see that for the equation of JJ is complete half of what we need for each of the section, which is AE, CE, AF, and CF. Now we need to complete the second half, which basically just loop JJ one more time using KK. So what KK do is we, instead of having the green box on the left, we move one time to the right, and at the same time we move the block from the top of the second metric B, move down by 1. So what I do is this is a new block for metric A, and this is a new block for metric B. So then the exact same thing happened again. You got 3 times 9, 4 times 13, and then you add that to the first column, which is before is 11. Now when you add the result of 3 times 9, 4 times 13, you get 90. And that is the exact result that we want for our final answer. And then we move one more time. We got 3 times 10, 4 times 14, and then you pass to the second part. Now we got 100. And then the same thing happened. We repeat this. We go down by 1, and then we add, go down by 1, then we add, go down by 1 more, and then we add. And then what happens is that we finish B, BG, and DG, and we add all together. So we get the first half of the metric C finished. Now, continue with the iteration of KK. We move the block to the right because the JJ got repeated one more time. So then we got 3 times 11, 4 times 15, add to this block. Now we got 110 and 120. And then the same thing happened again. We move down one row, we time to the same block, and then we add. Move down one row, time to the same block, and then we add. And so we finished our formula for our matrix C, and that is the final result for our 4 times 4 matrix with using blocking multiplication.
Okay, so now that we know how this code works with 4 times 4 dimension, now we're going to look at how we're going to apply this code with a matrix dimension of 22,200 by 2,200. Now I know the assignment asked for 22,000 by 22,000 matrix, but my computer simply can't generate a matrix that big. with Python. So yeah, so we're gonna look at 2200 by 2200. It's only by a factor of 10, so the performance should improve the same way. And now as you can see here, I made the B size 100. So why 100? Now the reason why we chose B size to be 100 is because through experimentation. So we experiment with B size 10 and we got 22.798 seconds. And we did with 50 and we got 20.28 seconds. So the performance improved by like 2 seconds. And after that we do it 100 and it improved by a very small amount, just 0.03 second. So it's very small. And we continue to try it again with 110, B size of 110. And now it's getting worse by 1 second. And then it gets worse by 0.1 second. But you get the idea that it's from performing better and then become worse and worse and worse. And at 440, it becomes 22.24 seconds. So now it's bad. So we look at here, we compare all of them, and we saw that V size of 100 is the fastest, even though if you compare 50 and 100, it's like very small. But we have to choose one, so we chose 100. And after that, we do profiling. We profile the result using gprof. And as you can see here, with multiply base, it takes 46.52 seconds if the matrix is 2200 by 2200. And here it says that it's taking up, basically saying that it's taking up 65.14% of the runtime. And but for multiply, it's only taking 24.83 seconds. And here it's saying it's 34.77% of the runtime. So it's much faster. It's 2 times faster when you do block matrix multiplication. So we can improve the performance even more, and we can improve it by using the concept called unrolling. So when we do unrolling, we're initializing more variables. So at first it's just double sum, but now we're gonna initialize variable called sum1, sum2, sum3, sum4, sum5. So actually there shouldn't be sum10, it should just be sum to sum9, whatever. But this is basically how unrolling looks like. And so we know that the B size should be 100, and now we test it with different number of unrolling. So when I say unrolling 1, I'm just saying like we ignore all these and we only do sum, basically what we did before, like only block matrix multiply, and we got 20.47 seconds, which is to be expected. But now if we unroll 2, that means sum and sum1 and ignore all these, and we got a 6-second improvement, which is a lot. So which is a lot of improvement. And then we continue trying, and with 5, unrolling of 5, we got 12.728 seconds, which is 2 seconds faster, which is also a good improvement. And by that I mean from sum to sum4. And then we try even more, so unroll of 10, and you can see here is 12.35 seconds. So the improvement is very minuscule, but it's a good improvement. And so that's basically this code here, from sum to sum9. So basically it's just doing multiple computation per loop. Yeah, that's the basic idea of it. Now why unroll of 10 and how does it improve the performance? So basically how it improves the performance is that it reduces the number of loop and increases the number of calculation per loop. So here you can see j plus 10, right? So it's looping every j plus 10. So it's gonna 0 to 10 and then to 20 to 30. It's not gonna be like 0, 1, 2, 3, 4, 5. So it's faster and it's doing more calculation per loop. So why can't we do more than 10 loop? Why does it get slower here? Well, that's basically because with too much unroll, it causes it fills up the instruction cache like too much. And so it will cause a lot of cache miss, which means it's gonna make the program go to the DRAM more, and that's gonna slow down the process. So here you can see there's a difference in number of instruction with no unrolling. There's only like, here you can see it's only 439 instruction before going to the main. But when you unroll 10 times, you can see that it's plus 2174. So it's like that many instruction, a lot more instruction than if you don't do unrolling and then go to the main. So yeah, there's more instruction, but it balances out well. So with the instruction cache size. So that's why it's gonna be faster. And here we can see the profiling of the result, the block multiply, B size of 100 and unroll of 10, number of unroll. And here you see base, multiply base is still 42.5 second, but for multiply it improved to 13.74 second. So if like now it's like about 4 times or 3 times faster. And you can see here multiply base takes up 75.56% of the runtime, but multiply only takes up 24.42% of the runtime. So it's a lot faster now.
In this section, we will compare the hit and miss of blocking and base multiply. For start with metric A, so we assume the worst case that the cache can only fit. No, each block size is only 8 bytes, so 2 in. So for the base case, we can see that if we want 0, 1, 2, 3, at first 0 and 1 we will be able to get into the cache with one compulsory miss. But when we need 2 and 3, we will need to replace 0 and 1 with 2 and 3. So we replace 0 with 2 and then 1 with 3. Because they cannot fit all 4 numbers into one block size. And that causes a miss hit, miss miss. And then if they're gonna continue the loop, it will result in always miss. But for blocking, we limit the amount of number going to cache so that it fit in the block size. So in this case, it's only 0 and 1 that go to cache, and we encounter one compulsory miss. And then the rest of the loop will hit because 0 and 1 is already in the cache. And because miss hit. For metric B, same case. For base, we access the memory on each column only once and replace it, just like in this diagram. So every time we go to a new column, we have to replace it, causing the program to consistently need to load number to cache. And this make the metric B for the base case to be always missed. Compared with blocking, we repeatedly use the same square box until it's done, and then we move to the new block. With this, the cache need to only make 2 compulsory miss, and the rest of the loop will hit because the block is always get looped and it's already in the cache. So basically, it's 2 miss, then the rest hit for each of the block that we needed. Now for metric C, for the base case, because we move 1 block at a time, and there's no loop anywhere, so it will always miss because there's no reuse of the position. But for blocking, there will be a compulsory miss on each of the line, and then it will hit. And then when there's reuse, the side that already acted will result in the hit because it's already in the cache. And demo time.
So first we're gonna check mm.h. So here, size X is 2200 and size Y is 2200. And it's actually should be 22,000, but it's too big, and yeah. So let's go back. Alright, so now we're gonna look at mm.c. So let's go back, go up. Okay, so here we have flush all cache. We didn't talk much about it in the slides, but basically what this does is it's gonna remove everything that is in the cache. So like from L3 to L1. So 18 megabyte, which is the size of L3. So when we do that and malloc the whole cache size and then free it later on, it's gonna remove everything that is in the cache. 18 megabyte. So L3, L2, L1 will be all gone. There won't be anything in it. And this is from a Stack Overflow. So here, load matrix base, free all. This is how we did multiply base, compare result, write result, and load matrix. We use the same thing as what Ajahn did. And here multiply. So here b size 100, n is size x. I mean n can be size y as well. Size x and size y should be equal. And here unloop, unrolling. Here's the effect of unrolling. And here's the quick run through to okay. So now we're gonna test it. Okay, here. So loading 0.43 seconds, and now let's see what's the time taken for matrix multiply for base. Okay.
Fast forward 40 seconds ครับ
Fast forward. Okay, so 39 seconds. So yeah, roughly 40 seconds. And same loading speed, 0.35 seconds. A little bit faster, but it should be the same anyway, actually. But okay. Oh, so you see here, multiply takes 12.8 seconds. So it's like about like 4 times faster, or 3 times, more than 3 times faster. So yeah, it's a lot faster now with unrolling and block multiply. So that's it for the demo. Thanks for listening and bye bye.
Bye bye